Hello, guys. Welcome to our first lesson in Unit 5. Today, we're going to be talking about buffers. It's something that a lot of us have at least heard the term. If you work in or around a pool, you've definitely heard of buffers. And then if you're in health sciences, you've probably talked about some of the buffers that exist in our body that keep certain levels regulated. So we're going to talk about today what buffers are, how we make them, and how they work. Okay, so I want to bring this back up because as I've mentioned before, the idea of buffers, so this next unit hinges on the understanding of how conjugate acid-base pairs work and their strengths, okay? So when in this list, we have acids, and then to the right-hand side, we have their conjugates, which of course are then bases. Except for up here at the very top, for our strong acids, this arrow doesn't even continue because their conjugates are weaker than water. You see water is this cutoff right here, right? So because they're weaker than water, they are not going to act like a base at all. So all of these up here are neutral. But then once we move past water, and so we've got the conjugates of what are now weak acids, then their conjugates begin to have basic characteristics, so they can act as bases. They are basic, right? And we even get to a point here where we kind of flip over the base. The conjugate base is going to be stronger than the weak acid because look, if we look at these Ka values, the Kb for these conjugate bases is going to be greater. So it's actually going to be a solution of the two would be basic at that point. Okay, so we've got to understand. Sorry, Mr. Barry just interrupted me. And I'm a minute and 40 seconds into the slide, so I don't want to start over. So if you're watching, you can text me on Remind and say, Mr. Barry, leave Miss Wilkins alone. So anyways, we've got to understand how these pairs work. All right, so reviewing that, the key concept was from the last unit was our salts, learning that a salt, which is an ionic compound, can be neutral, acidic, or basic, right? And so if a strong acid and a strong base created the salt itself is neutral. If a strong acid and a weak base created the salt is acidic. If a weak acid and a strong base created the salt is basic. And then if a weak acid and a weak base created the salt, then the two ions could compete. And so we have to actually compare their K values to see which one would win out. Okay, so that's a major, major thing from last unit that you've got to make sure that you understand. Okay, so what is a buffer? A buffer is a mixture of a weak acid or a weak base with its conjugate salt. Now, we say it's conjugate salt because I can't just throw in acetate ions, which is the conjugate of acetic acid. What I can do is add sodium acetate. So I've said this a lot, right? Like we can't just add ions. We got to add the salt. That's the source of the ions. So it's a mixture of a weak acid or a weak base with its conjugate salt. So the important thing, super important thing right here is that they are weak. Okay? And you're going to see why that's important in a moment. So what does a buffer do? If we look at this example here in the picture, when I add hydrochloric acid to just pure water, my pH is obviously going to go way down. It's going to become acidic. But if I add HCl to a buffer, the pH is going to stay relatively the same. We went from 7 to 6.9. Same over here, if we add a base to pure water, the pH is going to go way up. It's going to become basic. But if we add a base to a buffer, it's barely going to change. It went to 7.1. So that's what buffers do. They resist changes in pH when adding small amounts of acids or bases. Now, eventually you could add enough acid or enough base that you're going to overcome the buffer capacity. We'll talk about that. But that's by definition what a buffer does. It resists changes in pH. It keeps pH relatively constant. Okay, so for example, we could have a buffer made up of acetic acid and sodium acetate. So there's a weak acid and its conjugate base. Again, we can't just add acetate, so that's why we have sodium acetate, but the sodium's neutral, so it's just a spectator. It's not going to do anything. And then ammonia and ammonium chloride, because there's ammonia, which is a weak base, and then its conjugate, ammonium, and the chlorine is neutral. So if you look at this example in this picture over here, this is a buffer. So it has carbonic acid, which is a weak acid, hydrogen carbonate, which is its conjugate base, and then it also has sodium in there, because the only way to get this hydrogen carbonate ion would have been to add sodium carbonate, hydrogen carbonate, okay? So that's why in a buffer, we're really going to have 4 parts, and you're going to see that. You're going to have the weak acid or weak base, water, which is not shown here, but it's clearly what this is all floating in, the conjugate, and then the spectator salt, okay? So how can we make a buffer? So we can make a buffer directly. We can add the 2 parts directly. So we can add a weak acid or a weak base and its conjugate salt. So for example, we can literally put acetic acid into solution, and we can put sodium acetate into solution. Why do we have to put sodium acetate? Because I can't just put acetate ions. Now, let's look at something for a second. What is the equilibrium equation for acetic acid? Plus water is going to donate that hydrogen to make the acetate ion. Sorry, I'm writing crooked because of the video thumbnails in my way. Okay, so that's my equilibrium. So students often wonder, okay, well, why isn't a solution of just acetic acid a buffer? Because if I just put some acetic acid in water, I've got acetate here. The issue is, remember, this is a small Ka. So it is very reactant favored. So the majority of it is going to remain the non-ionized version. The majority of it is going to remain HC2H3O2 acetic acid. So if we need to have a equal or at least significant amount of acetate, I can't rely on this acetic acid to produce it. I have to actually add it in. This is also a time to point out why it has to be weak, okay? If this were HCl, which is a strong acid, what do we know about strong acids? They 100% ionize. So there is no equilibrium. Every bit of it becomes the conjugate and hydronium. And there's 2 issues here. Number 1, in a buffer, we need those 2 parts. We need the acid and the base. Well, this acid is no more. It's all become chlorine and hydronium. Second problem, chlorine can't act like a base. It's neutral. So we absolutely have to use weak acids or bases in buffers. And then we have to actually add in a significant amount of their salt. So that's how we directly make a buffer. We do a weak acid and then its conjugate salt and put them together in solution, or a weak base and its conjugate salt and we put it together in solution. Another way we can make a buffer is indirectly. We can produce the conjugate through an acid-base reaction. And here's what I mean by that. So in this example, it says add 50 milliliters of 0.5 molar sodium hydroxide to 50 milliliters of 1.0 molar acetic acid, okay? So what reaction is going to go on here? So we've got acetic acid, plus NaOH. Now, sodium's not going to do anything. I'm going to leave it out. It's a spectator. It's a net ionic equation. And hydroxide is strong, so there is no equilibrium. every bit of that hydroxide is going to remove a hydrogen to produce the acetate ion and water. This is just your typical acid-base reaction. We have an acid, base, making a salt and water, right? Because technically that's sodium hydroxide makes sodium acetate, but we know that sodium is a spectator, it doesn't do anything, so we just leave it out. It's not part of the reaction, okay? So how does this create a buffer? Well, if I have 1 molar of acetic acid, I have 50 milliliters of it. I'm going to convert this to moles. We talked about this in class. So I'm going to convert this to moles by multiplying by liters. And I have 0.05 moles of acetate, right? And now if I want to convert that back to molarity, 50 plus 50 is 100. I got to divide this by 0.1. And so now I have 0.5 molar. This up just a little bit. 0.5 molar acetate. Okay? Acetic acid, I'm sorry. So then I added 0.5 molar of hydroxide, 50 milliliters of it, which is 0.05 liters. So I multiply that and I get 0.025. Sorry, I always get nervous when I'm doing mental math and I'm going to do it wrong. You're going to make fun of me. 0.025 moles. And then now I have 100 milliliters, so I'm going to divide that by 0.1 liters. And now I have 0.25 molar. Okay? So first what I did is I took care of the fact that my volume changed. And so I needed to adjust my molarities in this new solution. Now we can think of this like an ice chart. What's going to happen? What's going to react? Well, I have less hydroxide than I have acetic acid. So all the hydroxide is going to get used up. So minus 0.25 minus 0.25 plus 0.25 plus 0.25, right? And now water doesn't really matter because that's already there to begin with. Now I'm left with 0.25 acetic acid, 0 hydroxide, and I now have 0.25 molar acetate. So what I did is I created a buffer by neutralizing half of my weak acid, which forms its conjugate base. So that's how we can indirectly create a buffer. All right, so whichever method we use, the important thing is we have to have a weak acid or base and its conjugate. Because, for example, if we have a weak acid, which means we have its conjugate base, if I add acid, it can react with the conjugate base to be neutralized. If I add hydroxide, it can react with the weak acid to be neutralized. We've got to have both parts so that I can keep pH the same whether I add acid or base. All right, and so we're going to look at what that looks like exactly. So if I have an acidic buffer, that means I have a weak acid with its conjugate base. So this is our equilibrium expression. We have that acetic acid plus water making acetate and hydronium, but this is going to be very, very reactant favored, which is why I explained you'd have to add in significant amounts of the acetate. So for a buffer, we've got a significant amount of both. If I add base to this, so I'm adding hydroxide ions, those hydroxide ions are going to react with the acid in this equation here, getting rid of that addition of hydroxide, which is going to keep the pH relatively the same. Okay? So I've had students ask in the past, well, wait a minute, hydronium would be a stronger acid than acetic acid, so why doesn't the hydroxide react with hydronium? Again, we've got to remember This is very reactant favored. So there is very little hydronium in this solution, while there's a ton of acetic acid. So it is the weak acid, acetic acid, that the hydroxide would react with. Now, if we have the same exact buffer, but this time I add an acid, which means I'm adding H3O+. The H3O+ can react with the weak base, the acetate ion, in this equation to neutralize that addition of H+ and restore back our pH. So this is kind of a chart that shows that. So here's our buffer. We have equimolar, which just means we have the same amount of acetate and acetic acid. So the weak acid and its buffer, or its conjugate. We've got both. When I add hydronium, it's going to react with the acetate ion to produce acetic acid. So my acetate ion is going to get used up a little bit, and I'm going to make some more acetic acid. If I add base, it's going to react with the acetic acid, which produces acetate. So my amount of acetic acid is going to get used up, so it's going to go down a little bit, while my acetate ion is going to go up a little bit. But if I look at the actual pH, it's going to stay relatively the same. But this also shows that if I kept adding acid and kept adding acid, eventually I would use up all of the acetate ion and I would make so much acetic acid that I would no longer have my pH the same. It would turn to be acidic, or it would go down further. And that's buffer capacity we'll talk about in just a minute. Okay, so now let's flip to a basic buffer. What makes it a basic buffer? It's a weak base with its conjugate salt. That's it. Okay, so the pH of this buffer would actually be basic. It would be a basic pH. So this would be if we wanted to keep things slightly basic, maybe a pH of 8, if that's what the conditions call for. So if I add a small amount of base, so I add hydroxide to this buffer, it can react with the ammonium ion, which is an acid, to neutralize that addition and keep the pH relatively the same. If I add acid, so I add H+, it can react with the weak base ammonia to neutralize that addition and keep the pH relatively the same. So no matter if we have an acidic buffer or a basic buffer, additions of acid or base are going to be neutralized by one of the parts, and it's going to keep the pH relatively the same. Okay, so let's look at a couple examples of buffers. So in this first one, I'm telling you that we have a solution of formic acid and sodium formate. So the first thing that you need to be able to do is look at this and say, okay, what species here are actually going to be part of the equilibrium that's going to be established in this buffer? So I'm going to have formic acid and water, because of course this is a solution. And we know, what do acids do when they come in contact with water? They donate a hydrogen. So they're going to donate that hydrogen, which is going to form the formate ion. And hydronium. So you notice I left out the sodium. It's a spectator, it's not doing anything, right? And I didn't just have formic acid, I had also sodium formate. So we're going to have substantial amounts of both the formate ion and the acetic acid. So if I add an acid to this solution, so I drop in some hydrochloric acid, what can react with it? Well, it's going to be the base. So we're going to have those hydronium ions will get neutralized by the formate ion, which is a base. Because it's a base, it says, hey, give me that extra hydrogen, which causes it to form back into formic acid and water. So that initial jump in pH would then be brought back to very close to where we started. Okay. if I added a base in, so I added, say, sodium hydroxide, and we're only going to look at additions of strong acids and strong bases so that you can assume it's 100% hydroxide or 100% hydronium. So then that hydroxide is going to react with the acid portion of this buffer, which is that formic acid. And so that acid's going to donate its hydrogen to form water and reform that formate ion. And so that initial increase in pH is going to be brought back down. And I realized earlier I said that increase, I should have said that decrease in pH because it got more acidic, then came back to be where it started. Now with adding a base, that initial jump in pH, it would come back down to very close to where it started. Okay, this time here I have a basic buffer. So what's going to actually react? Well, chlorine is neutral. So I'm going to have the ammonium and water, and it's going to form, ammonia and water is going to form ammonium and hydroxide. So that's why it's a basic buffer. The actual pH of the solution would be a basic pH. So now if I add an acid, it's going to react with the base that's present. So NH3 plus H3O plus, it's going to neutralize that added acid by reforming the ammonium ion and water. So now that initial drop in pH is going to bring it back to close to where we started. If I add a base, it's going to react with the acid portion. So hydroxide, definitely not OH minus or OH plus, plus ammonium. It's going to take away that extra hydrogen and make NH3 plus water. So in this case, that initial jump in pH is going to bring it back down to close to where we started. So I've been mentioning this idea of a buffer capacity, and this is the last thing for this lesson. So the buffer capacity is the actual amount of acid or base that can be added to a buffer before the pH changes significantly. And typically we define a significant change is by 1 unit. So what I mean by that is if our starting pH was 6, if I go past 7, or if I go past 5. So within plus or minus 1, I'm within my capacity. If I go beyond that, either way, I have broken the buffer capacity. So for example, if I had 1 liter of 1 molar acetic acid and 1 molar sodium acetate, that's going to have a greater buffer capacity than 1 liter of 0.1 molar acetic acid and 0.1 molar sodium acetate. Because in the 1 molar example, we have 10 times the moles of the acid and the base, and so it could withstand greater additions than the one that had 10 times less. Okay, so buffers do have a certain capacity, and eventually they will stop working. Okay, I hope you have enjoyed this buffer lesson, and I'll see you next time.